Hey, this is Charlie Thompson, and welcome to the Lab 2 Too Long Didn't Read summary video for Lab 2. It's on Earth-Sun relationships and day length. So let's take a look at some of the really important parts, just the important parts. So Lab 2, what is the point? When you're done with this lab, you should be able to label a diagram representing Earth-Sun relationships in the annual march of the seasons. So you should be able to label a diagram as being an equinox or a solstice. You should also be able to calculate day length for selected locations for the solstices and equinoxes and analyze the relationship between latitude and seasonality. So seasonality refers to seasonal change, it refers to changes in the angle of the sun, and it refers to changes in day length, and there's a relationship between seasonality and latitude. That's part of the whole point of this lab. So there's Earth, and I've drawn in this line to represent Earth's axis. I've put these 5 lines to represent the 5 very important lines of latitude. There's the equator at 0 degrees. And the rest of the lines of latitude, the rest of these 5 red lines are all very important. They're very special. And they are all the result of Earth's axial tilt. So in the other videos for this lab, I've got a whole bunch of videos of seasons, what causes the seasons, what it looks like during the different seasons. So after you watch those, this will make different sense. The red line here indicates the position of direct rays from the sun. So if this is the way Earth orbited the sun, with Earth's axis 90 degrees relative to its orbit around the sun, then hopefully you can tell if this represents light from the sun, the only place on Earth that would get sun hitting Earth at a 90-degree angle would be the equator. So in this diagram, the subsolar point is the line of latitude that is getting sunlight at a 90-degree angle. The subsolar point is the line of latitude that the sun is directly over. So if Earth orbited the sun without any axial tilt, the only place that gets direct sunlight would be the equator. So the subsolar point would always be the equator. But that's not the way Earth orbits the sun. Earth is tilted 23.5 degrees relative to the plane that it orbits the sun. Because Earth is tilted 23.5 degrees, that throws those 4 other lines off by 23.5 degrees. So let's start. This is the Tropic of Cancer. It is the highest latitude that you can go and still get direct sunlight. So the tropics represent as far north and as far south as you can go during the course of a year and still get the sun hitting the surface at a 90-degree angle. In between the tropics, the Tropic of Cancer at 23.5 degrees north, the Tropic of Capricorn at 23.5 degrees south, their latitude is set by the tilt. The latitude of the tropics just equals the latitude of tilt. The other two, the Arctic Circle and the Antarctic Circle, they also have to do with day length. The only place you can ever get direct sunlight is between the tropics. So once you're out of the tropics, you can never have direct sunlight. If you're north of 23.5 degrees, if you're south of 23.5 degrees south, you will never experience the sun hitting you at a 90-degree angle. There's another interesting thing that happens, though, and in this picture, this is the December solstice. The subsolar point is the Tropic of Capricorn, and above the Arctic Circle, they have 24 hours of darkness. Below the Antarctic Circle, they have 24 hours of daylight, and the location of the Arctic and Antarctic circles, those are 23.5 degrees away from vertical, or away from the North Pole, rather. So 90 minus 23.5 is 66.5. So the Arctic Circle, 66.5 degrees north, the Antarctic Circle, 66.5 degrees south. So the positions of the Antarctic Circle, the Tropic of Capricorn, the Tropic of Cancer, and the Arctic Circle all are influenced and set by Earth's axial tilt, which is 23.5 degrees. Okay, So let's go through the 4 seasonal events, and I'm going to refer to them not as the summer or winter solstice, but the June and December solstice, because if it's the June solstice, it's summer in the northern hemisphere. The subsolar point on the June solstice is the Tropic of Cancer, 23.5 degrees north. That happens around June 21st. It's off a day or two every year, but for my classes, lecture, and lab, June 21st is great. Just remember June 21st, 3 months later, September 21st, 3 months later, December 21st, 3 months later, March 21st. So just remember the 21st. Every day it's different by a little bit, but don't worry about it. 21st is close enough. So on the June solstice, everybody north of the Arctic Circle has 24 hours of daylight. Everybody south of the Antarctic Circle has 24 hours of darkness. The equator always has a 12-hour day. If you are between the tropics every day in terms of day length, in terms of temperature, it's pretty much like every other day. In between the tropics, in this region, every single day, the day length is just about exactly the same as every other day. So that's one of the important aspects of seasonality is seasonality increases with latitude. If you're at the equator, the sun's always more or less overhead and every day is more or less 12 hours. On the other hand, at the North Pole, on June 21st. In fact, from March to September, they're at the North Pole from March to September, they have 24 hours of light, pretty much. And then at the South Pole, from September, or rather at the South Pole, yeah, that's right. From September, October, November, December, January, February, March, they have 24 hours of darkness. So June 21st, it's the June solstice. It's the longest day of the year in the Northern Hemisphere, pretty much. The equator still has 12 hours of daylight. 3 months later, it's September 21st, the September equinox. The subsolar point is the equator. Everybody all over the world has a 12-hour day. Everybody all over the world has a 12-hour day on the equinoxes. Equinox actually means equal night. So equal day and night equinox. 3 months later, it's December 21st. Oh, sorry, there's the subsolar point. Ooh, that's dramatic. December 21st, now the northern hemisphere is facing away from the sun. The subsolar point is the Tropic of Capricorn. So everybody south of the Antarctic Circle, they have a 24-hour day. Everybody north of the Arctic Circle, they have 24 hours of darkness. The equator still has a 12-hour day, 12 hours of daylight, 12 hours of night. And then 3 months later, we're back to the March equinox, in which everybody all over the world has a 12-hour day. All right, so that takes care of the location of the subsolar point during the year. We've got the 4 dates for the seasons, March 21st, June 21st, December 21st, and back to March 21st. The next thing I want to talk about is changes in day length. So one of the aspects of seasonality is changes in the length of the day. And at the equator, pretty much don't have any. The other aspect, changes in angle of the sun, that's going to be in Lab 3. So Lab 3 will pick up with seasonality. So everything we're talking about in this lab, you got to remember it for the next lab. That's one of the ways all of our labs are going to work, is you don't get to forget it. It builds. This class is going to build on itself. So what you learn in Lab 1, you're going to be losing. What you learn in Lab 1, you'll use in Lab 2. What you learn in Lab 2, you'll use in Lab 3. Physical geography lab is an accretionary process where you just keep learning stuff. It's not like many other classes where you cram for the exam and then forget it. You can't do that in geography. So back to changes in day length. Changes by latitude. So at the equator, everybody has a 12-hour day every single day. As you move away from the equator, for example, at 40 degrees north where we are, there's about a 6-hour difference between the longest day in the summer and the shortest day in the winter. So that at our latitude, 40 degrees, there's about 6 hours difference between summer and winter. And then by the time you get to the Arctic Circle, everybody north of the Arctic Circle has 12 hours of darkness and 12 hours of daylight during the year. So the difference in day length above the Arctic Circle or below the Antarctic Circle, it's 24 hours difference. The other aspect is that seasonal change doesn't occur at the same rate throughout the year. There's super fast change around the time of the equinox. The angle of the sun changes and the day length changes. Around the equinox, you'll see for us, the sun, for the spring equinox, we're gaining about 2.5 minutes every single day. And then at the fall equinox, every day we're losing about 2.5 minutes every day. So very, very, very rapid change at the equinox and almost no change at the solstices. You'll see this when you look at the time and date, and they talk about the change in day length from one day to the next. You'll see around the time of the solstices, maybe a second, less than a second change. And in Lab 3, you'll also notice around the time of the solstice, the angle of the sun, almost no change. So that covers changes in day length as a function of latitude and also changes in day length during the seasons. So you'll be using this website, timeanddate.com. Click there, go to it, and some of the user controls that you have, this link I just sent us to January. We're going to be using 2021, our latitude 40 degrees. It's close enough. So it's got this really cool diagram. It's got this really, it's got a summary view. So it tells us, like today, 9 hours and 53 minutes. Today, daylight, 9 hours and 53 minutes. Tells us what time the sun came up today, what time the sun is going to set. This is a graphic. So I go over this in more detail. The blue part is daytime. This is nighttime. So you can see the difference between winter and summer day length. And you could actually move across, and if you're really good, you could probably find June 21st, and that's going to say that the day length is 15 hours, 1 minute. December 21st is the winter solstice, the December solstice, and the day length, 9 hours, 20 minutes for Sacramento. So as you scroll down here, these are days, so like the 7th, today. So today the sun came up at 7:15. The sun's going to set at 5:08. This right here tells us day length, 9 hours, 53 minutes, 28 seconds. And this is the change to day length. And if you move up, it'll say day length, length, and difference. And so today is actually 1 hour and 50 seconds. I'm sorry. Today is not 1 hour and 50 minutes. Today is 1 minute, 50 seconds, almost 2 minutes longer than yesterday. And you can see that's changing. On January 1st was 42 seconds longer than December 31st. By the time we get to the end of the month, it's going to be 2 minutes and 6 seconds longer. I can't resist going to March. Around the time of the equinox, 2 minutes, 38 seconds longer. 12 hours, 12 minutes. We get about 8 minutes extra sunlight because of refraction, the bending of the sun's rays as they enter the atmosphere. So about a 12-hour day. And that's pretty much it for this lab. That should take you through how to use time and date to find for any, there's the month, there's the year. Oh, and the latitude. Yeah. So about the latitude, I've given you links for everything, but another way to do that is you can just hack the latitude. The first number, 40, is the latitude. The second, -120, that's the longitude. So the 3 places that we're going to be looking at are 40 degrees north. We're also looking at 20 degrees north, and we're also going to be looking at 60 degrees north. And then you can see how the shapes, like at 60 degrees, you're almost up to the Arctic Circle, so it never gets totally dark in the summertime. It just goes to twilight. The sun goes below the horizon, but let's see, day length, the day for June 21st. Oh yeah, you've got to look that up. I'll let you look that up. That's part of the assignment. Yeah, okay, so that really does cover everything that you need to know to get started on this assignment. If you have any questions, come to the Zoom sessions. If you have any questions, feel free to call me, text me, or email me. And yeah, I hope you enjoy this lab.